Good morning, students. So today we are starting new chapter, right? Thermodynamics. 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 We can break this word into two. Thermo means heat, and dynamics. Dynamics we have studied in 11th standard, where laws of motion, right? Laws of motion is called dynamics. So that means motion, heat, and motion. That means motion provided by heat is thermodynamics. Okay. So does it mean that it is only related to gas? Can be related to solids. It can be related to liquids. And yes, it is related with gas, and that is what we are going to study. Okay. Thermodynamics that we study mainly is with gases. Right? So in thermodynamics, what other things we are going to study? What is going to change? Like in dynamics of mechanics, we were having, there was velocity, there was acceleration, there was force. So here what we are going to study. So here thermodynamics mainly is concentrated on macroscopic properties of the gas. Okay, we are going to talk about macroscopic properties. Discussion about macroscopic properties. Okay, the question is, what are macroscopic properties and what are microscopic? Microscopic means is which are at molecular level. Okay, macro means on the larger level, not at that small level like molecules. Okay, so what are macroscopic? Macroscopic properties means is we are going to discuss about pressure, we are discussing about volume, we are going to discuss about temperature, we are going to discuss about mass, okay, and we are going to discuss about number of moles. So these are macroscopic properties. We are not going to talk about molecules here, not required. Okay, molecules will talk, but in kinetic theory of gases. There we talk in terms of molecules also. Okay, but here we will discuss mainly with these properties, right? Okay, so P, V, T, M, and N, right? This is how we represent them, correct? Okay, then what is the first thing? As in laws of motion, we saw there were laws. Here also laws are there. Okay, but before going into the laws also, there are certain things we should understand. A new chapter always has a new terminology, new terms. Okay, so we need to understand that. So first thing that we are going to discuss now is thermal equilibrium. What is thermal equilibrium? Thermal equilibrium. Now before thermal equilibrium, we have studied equilibrium, right? In mechanics, we studied equilibrium. What was equilibrium there? Net force is zero, translation equilibrium, net torque is zero, rotational equilibrium. Okay, if combine both, then total equilibrium we can say. Neither force is there nor torque is there. Okay, so thermal equilibrium means what? Thermal equilibrium, if we are going to concentrate on the gases, we are concentrating on the gases. So, if macroscopic properties of the gas do not change with the time, then the gas is in thermal equilibrium. If all the macroscopic properties of the gas do not change with the time or remain constant, then the gas is in thermal equilibrium. Okay? If all macroscopic properties of gas remain same or constant, does not change with time. Does not change with time. Then the gas is in thermal equilibrium. Gas is in thermal equilibrium. This is thermal equilibrium. Okay. Thermal equilibrium does not mean only that the temperature of the two gases is same. We'll discuss that actually. Okay. So all the macroscopic properties of the gas need to be constant, then only we'll be saying that a particular gas is in thermal equilibrium. So how can we make sure that a gas remains same over a period of time? We can do that. What we can do is we can keep the gas as an isolated container. Okay. Such a container in which the external interference is not possible. Right. Suppose we keep on this container here. Let's keep this as a container. This is a container. Isolated it is. It's not in contact with anything, but certainly atmosphere is there, right? Surrounding is there. So what you'll do is we'll make sure that no heat is coming inside. So we'll make boundary like that. So we'll make it this is insulated container. This is insulated material. So that heat cannot pass from outside and heat cannot go from inside to outside also. Maybe inside temperature is more, outside is less. So heat can go outside. Because we all know that, right? Heat is what? Energy. And this energy flows from higher temperature to lower temperature. Correct or not? Heat is energy flows from higher temperature to lower temperature. If higher temperature is outside, it would like to come in. And if higher temperature is inside, it would like to go out. So what we have done is we have made this as insulated container. This is insulated. Insulated container. Now insulated means is insulator. Insulator means is current cannot pass through that, right or not? So all good electrical insulators are good thermal insulators also. Okay. So here we have taken insulator, and in terms of heat, we call this as adiabatic boundary. Adiabatic boundary. That means heat cannot pass through that. Both are same, insulated container you say or adiabatic boundary you say. So this is adiabatic boundary. Okay. So heat cannot pass through this. Fine. Now we have a gas inside. There is a gas. There is a gas over here. Okay. Like this gas is there. Dots only there. Okay. So suppose that its pressure is P, volume is V, temperature is T, mass is M, and number of moles are M. Anything has changed? Nothing. No heat is flowing. Pressure is same. Pressure, who's giving the pressure? Basically, pressure is because of temperature only. Because of the temperature, these molecules of the gas are getting kinetic energy, they are striking these walls and creating the pressure. And since temperature remains constant, kinetic energy remains constant for these molecules. So, pressure also remains same. Volume is constant, it's inside the container. And gas always occupy whatever amount of volume is available to it. So, whatever is the container's volume, same is the volume of the gas. Mass is also same because it's not leaking outside, number of moles, same. So, all the properties of this are same. Okay. So, we can say that in this case, the gas is in thermal equilibrium. Okay. We made it in thermal equilibrium. Okay. So, gas is in thermal equilibrium here. Same thing we can do when we are going to have two gases in two chambers, both are connected, but in between there is adiabatic partition. That means insulated partition. So again, we can say both the gases are in thermal equilibrium. Okay, they can be in thermal equilibrium, even though their temperatures can be different. I'll show you that. First you note this fast. Right? Let's see. The same thing we are going to see now. In that one, I am going to take two containers. Let's take two containers over here. What happened? Right. So two containers in this we are going to make. Okay. This is the separator, which is adiabatic separator. This is adiabatic separator. And it's isolated chamber. Anyhow, it is isolated everywhere. It's not transferring anything to surrounding also. Okay. This is also adiabatic. Right. This is also adiabatic. So two gases we are keeping. In this one also one gas is there, in this one also one gas is there. Okay. This pressure is P1, its volume is V1, its temperature is T1, mass is M1, number of moles are N1, and here also V2, V2, T2, M2, N2. Now the question is, are they able to interact with each other? No. Is this fixed? Yes, this is fixed. So they cannot change the volume either. So they can be like this forever. Yeah, no problem. So under these circumstances, we can say this is also in thermal equilibrium, this is also in thermal equilibrium. Okay. So it's not necessary that we should be saying that temperature should be same. Where temperature should be same, that we have to understand. Then only in thermal equilibrium. We'll see that. Okay. So that is basically who gives us the idea about thermal equilibrium? Zeroth law. For that only we were doing all this till now. So let's discuss zeroth law. Let's understand zeroth law. Where and in what circumstances zeroth law is applicable, where it is said that about thermal equilibrium, that we have to discuss. Okay. So thermal equilibrium is given by zeroth law. Zeroth law, why zeroth law? Zeroth law because first law of thermodynamics came first, then came second law, and zeroth law came last. But it is very important because it talks about thermal equilibrium. It's a very basic thing. So that's why it is brought before and called zeroth law. Okay. So what zeroth law is? Zeroth law. Okay. So if you go to the definition is very easy. It says that, let's say an object A. Okay. An object A is in thermal equilibrium with an object B, or gas also you can say. Gas A is in thermal equilibrium with gas B. And another one, gas C is also in thermal equilibrium with same B. Then C and A are also in thermal equilibrium with each other. Now thermal equilibrium, I told you, what is thermal equilibrium? Pressure, volume, mass, number of moles, temperature should remain constant, okay, for the period of time. Then we will say that they are in thermal equilibrium. Okay. So what it says that if gas A is in equilibrium with gas B, gas C is also in thermal equilibrium with gas B, then A and C also will be in thermal equilibrium. Okay, understood that? Let's try and understand this. But this is applicable in which case? First I will make the container and I will try to show you. Okay. So how it is? Just see. Okay. Right. So we'll make the container first. Okay. Now this is adiabatic wall, right? This is adiabatic. Here is gas A and here is gas. They cannot interact. Okay, and the gas is also not going anywhere. It is also packed. Same as here also. Right? Above them, we are keeping gas P. Like this. And this here, this is a conducting partition. Okay, this is conducting partition. And we are calling it as diathermic wall. Okay, this we are calling as adiabatic, this is called diathermic, from where heat can pass. Okay, so this is diathermic wall. Right, so what will happen? Initially, maybe their temperatures are different. In this one, what is going to happen? See then, okay. Suppose its temperature is TA, initially its temperature is TC and its temperature is TB. So what will happen if suppose that temperature of A is more than temperature of B? Heat will flow from here to B. Okay, so then it will continue to flow till both temperatures are becoming same. Now exactly same thing is going to happen between B and C also, because there is a conducting separation. So from here also the heat exchange will continue till these two are becoming same, right? So if we say that A and B are in thermal equilibrium, that means from here now no more heat is going to B, or from B no more heat is coming to A. Same way, no heat is going from C to B and from B to C. Okay, so these two are in thermal equilibrium, these two are also in thermal equilibrium, that means these two also will be in thermal equilibrium. But this is applicable in which case? When there is conducting separation. So far we were talking about what? Insulating separation. So if insulating separation is there, these two gases we can say are in thermal equilibrium even though their temperatures are not same, right? But in this case it is not so. When the conducting separation is there between the two gases, then two can be in thermal equilibrium only when their temperatures are same. Okay. So what zeroth law says? Zeroth law statement is, what is the statement? If gas A is in thermal equilibrium with gas B and gas C is also in thermal equilibrium with gas B, then gas A and gas C are also in thermal equilibrium. Okay, this is zeroth law. So I hope you understood that what is the meaning of thermal equilibrium as such. Okay, so that law is applicable for this only. So don't, without seeing the question, don't write the answer. Okay, if this kind of a question is given and he asks that what is the meaning of thermal equilibrium here T1 is not equal to T2. Okay, but if this is the case in which boundary is conducting boundary, then temperatures of both need to be same for thermal equilibrium. Okay, note this one fast. Right? This is about zeroth law and thermal equilibrium. Now, what's next? The next thing in this one is internal energy. Say internal energy of the gas. Okay. What is internal energy? Right. So internal energy, normally we talk about what type of energy? Mechanical energy, we say kinetic energy and potential energy. Okay. So here also, internal energy also will be kinetic energy and potential energy. So kinetic energy what? Okay. Kinetic energy, when we talk about kinetic energy of gas, kinetic energy means what? Kinetic energy means it's related to the molecules of the gas. The molecules will be moving. Okay. So kinetic energy can be, how can they move? That is also a case here. Kinetic energy can be translatory. Molecules can move in translation. Molecules can move in rotation also. There's rotational kinetic energy also. And there can be vibrational kinetic energy also. Okay. Particles can move, can do oscillation. Okay. So kinetic energy of gas can be in three forms. Kinetic energy of translation, kinetic energy of rotation, kinetic energy of vibration. But kinetic energy of vibration, normally we don't take. We don't talk about kinetic energy of vibration. Okay. So we are limited to two types of kinetic energy, translation and rotation. Vibration kinetic energy takes place at very, very high temperature. Okay. And that is, we are not including, it's not in our syllabus also. We are not discussing about kinetic energy of vibration. Unless it is given exclusive in a question, then we'll think about it. Otherwise, we are not discussing. So kinetic energy of the gas, we are having two forms, kinetic energy of translation and kinetic energy of rotation. So it is there. Kinetic energy is having this form. Okay, molecules are moving in translation also and rotation also. Fine. Then what about potential energy? Potential energy of gas is possible when we are going to consider molecular attraction or molecular force rather, don't say attraction or repulsion. Molecular force. One molecule is exerting force on the other one. Then we have to talk about potential energy also. Okay, due to interaction between molecules. Interaction between molecules. Okay, but when we talk about ideal gases, in ideal gases it is clearly told that the assumptions that we have for ideal gases, that they don't have interaction between molecules. Okay, for ideal gases this interaction is not allowed. So that means potential energy we don't have to consider, right? So I am writing it for ideal gases. There is no interaction between molecules. Okay, so for ideal gases, potential energy become 0. Okay, so the potential energy is 0. So then, what is internal energy? So internal energy comes to kinetic energy. Internal energy is what? Only kinetic energy. Okay, note this one. Right? So internal energy of the gas, ideal gas, is the kinetic energy. Okay? Internal energy of ideal gas is equal to kinetic energy of ideal gas, obviously. Right? Fine. So we have a clarity now that whenever we are talking about internal energy, it is kinetic energy. Okay, fine. Understood. Now, to find out the formula for kinetic energy, to find out the formula for internal energy, we require certain other terms that we have to understand as well. What are those? Degree of freedom. Okay, degree of freedom. Okay, so what are we trying to understand? Internal energy. Internal energy means kinetic energy. So degree of freedom is related to that. That is going to give us idea about kinetic energy. Yes. Now, what is degree of freedom? Now, degree of freedom is defined for different type of gases. Different type of gases means there is monoatomic gas, there is diatomic gas, and then there are polyatomic gases. Okay, so every gas is having different degree of freedom. Okay, so how to find out? Basically, degree of freedom means what? Degree of freedom means is if you talk about a molecule of the gas, what are the possible ways in which kinetic energy, or rather the motion of that molecule, can be expressed? Is degree of freedom. Okay, number of possible ways in which the motion of that molecule can be expressed. We'll call it as degree of freedom. Okay, so number of possible ways in which a molecule of gas can move is degree of freedom. Okay, now let's talk about monoatomic gas to start with. So monoatomic gas is what? Monoatomic gas means a single molecule is there. Single molecule. A single molecule when given temperature, now it cannot store the energy. Okay, so what it will do? It will start running. Which way it can run? Say it can run along x-axis. It can run along y also, and it can run along z also. So what it is doing? Translation. It's doing translation. Translation along x, translation along y, translation along z. So translation, it has 3 degree of freedom. Okay, because in 3 along 3 axis it can move easily. So 3 degree of freedom. How many types of kinetic energy we saw? Translation and rotation. So translation, it has 3 degree of freedom. What about rotation? We said that rotational kinetic energy is not involved in this. Why? A single molecule. Single molecule, when we talk about, if the axis is going here, and it's a molecule, okay, size is very small. Very small. Single atom. Okay. So atom size is what? Atom size, if we consider that radius is 10 to the power minus 10. But we know that atom means is basically we are considering electron also. But where the mass is? Mass is a nucleus, that means radius very small. So what will be its moment of inertia? 0. Almost. So moment of inertia itself is 0. Kinetic energy of rotation, if I write, it is half I omega square. Okay, that's why I is required. So I is 0. So kinetic energy of rotation we are not considering, at least in monoatomic gas. Okay, so in monoatomic gas, how many degrees of freedom are there? Only due to translation. Okay, so degree of freedom of monoatomic gas is due to translation. Okay, because of translation 3 and rotation 0. So total degree of freedom for monoatomic gas 3. Okay, 3 degrees of freedom. Right? Note it. Done? Okay. Let's go to diatomic gas then. Diatomic gas means what? Two atoms. Okay. So diatomic gas. So when we have two atoms, make it like this. Okay, two atoms. Giving heat to them. Which direction they can move? They can move along X, Y, and Z. What is the problem in that? So translation. When you talk about translation, they have all 3 degrees of freedom. They can move in all the directions. Okay. X, Y, Z, anywhere they can move. Along X like this, along Y like this, along Z like this. There is no issue. Right? Translation, 3 degrees of freedom. Rotation. Now, its rotation, is it going to be more than what we got for monoatomic? Because for monoatomic, whatever we got, we said that it is 0. That means that is a reference for us. Normally for potential energy measurement, we'll take reference, no? It's always a comparison, right? So that we said 0. So is it more than that? If it's more than that, we are going to consider. Otherwise, here also we'll say that not possible. Okay. So let's talk about rotation. So in rotation, what? We have two atoms like this. So what can happen? We can make our axis pass through this in this way. So is its moment of inertia will be more than what we calculated in the previous case? Answer is yes. Yes, because the entire atom is outside of this axis of rotation. So definitely here this R is a lot more than what we got in the previous case. This R is also more. No doubt. So along y-axis definitely moment of inertia is there. So we will consider rotation along y-axis. Then z-axis, if z-axis I consider like this means it's perpendicular along z-axis. Along z-axis also, it can move in this way. Along y-axis, how it was moving? Like this. Along z-axis, like this. Okay. So in this one also, same R is there. This is R, this is R. So here also considerable it is. So along z-axis also possible. Okay. Along y-axis, it's possible. Along z-axis, possible. Along x-axis, if I am seeing, then again it is the same case as it was in monoatomic. This will be the x-axis. And it's passing through the atom. So if it's passing through the atom, again, moment of inertia about x-axis is 0. But moment of inertia about y is not 0 and about z is not 0. So two types of rotation possible here. So we will say that degree of freedom of rotation also 2 here. Okay, how much? 2. So total degree of freedom 3 plus 2, 5. Okay. So total degree of freedom for diatomic gas. How much? 3 plus 2, that is 5. Clear? Note it. Right? Then what else? I said polyatomic gas. So polyatomic also we will see. Now, polyatomic means more atoms, right? So let's say after 2 what is the minimum? 3. So let's say 3 atoms. Okay. So 3 atoms are like this suppose. Okay, we are taking in this way. A triangular shape I have taken, non-linear. Okay. So now, if we are giving them heat, then how they will proceed? Along X, along Y, along Z. There is no problem. Translation. Okay. Translation. Translation, there will be 3 degrees of freedom. Along X also. Along Y also. And along Z also. Okay. Along X it is there, along Y it is there, along Z it is there. So that means translation will be 3 degrees of freedom. Right? Then what about rotation? Rotation, if we see, so it depends on where is the axis, x axis, y axis, z axis. So if suppose we already have taken its triangular, okay. So in triangular, if I am going to consider, here are atoms, right? So let's talk about y axis. So let's say y axis is passing through this. These two atoms you can see, they are away from this axis. So that means what? They have moment of inertia. Okay. So along y axis, moment of inertia not zero. Not zero, sorry. Okay. Then z axis. Z axis we can make, again we can make it pass through this also. Like this also we can make. So if its axis is passing through this, then definitely this is having moment of inertia. This is also having moment of inertia. So that means along z axis also it is not zero. Iz is also not zero. What about x? Let's say x is also passing through that atom only, like this. So again, these two atoms are away from this axis. Again, moment of inertia is there. So Ix is also not zero. So that means moment of inertia is there for all three axes. That means rotational kinetic energy, degree of freedom will be what? 3. So this is also 3 here. So total degree of freedom is how many? Total degree of freedom is 6. Total degree of freedom 6 here. So monoatomic gas degree of freedom 3, diatomic gas 5, polyatomic gas 6. Okay, note first. Then, okay. So degree of freedom also we got. But so far, where is internal energy? Huh? Okay. Now let's see law of equipartition of energy. Okay. Law of equipartition of energy. Okay. So what it says? It says that every degree of freedom has equal amount of energy. Law of equipartition of energy says every degree of freedom for a gas is having equal amount of energy. And if we talk in terms of molecule, then every molecule of the gas will have equal amount of energy associated with the degree of freedom, and it is equal to half kT. Okay. Every molecule of gas has equal amount of energy associated with each degree of freedom. Okay, every molecule of gas has equal amount of energy associated with each degree of freedom. So if it is having three translation kinetic energy, so along x-axis, along y-axis, along z-axis, the energy associated with them will be same. Okay, and with each degree of freedom, how much energy? Each degree of freedom has energy equal to half kT. This is for molecule, okay? I am talking only about molecule at the moment, not about the entire gas, only about molecule. So half kT, okay? Half kT. Now how many molecules will be there? N molecules will be there, right? So half N kT. Now question is this, what is this K? K is Boltzmann constant. What is K? K is Boltzmann constant. Boltzmann constant. And what that is? K actually equal to R by N. This is Na. Okay, Avogadro number. So then this is also Avogadro. Okay. K equal to R by Na. R is what then? Universal gas constant. Okay. R is universal gas constant. Universal gas constant. And what is its value? R value, we all know that. Yes or no? R value, we all know. So K is equal to R by Na and R is equal to 8.34. Right? Then after that, joule, then per mole per Kelvin. Okay, so 8.34 joule per mole per Kelvin. That is the value of R. K is what? If you keep the value of Na, which is 6.023 into 10 to the power 23, then its value will come 1.38 into 10 to the power minus 23. Okay, joule per Kelvin. Okay, that's Boltzmann constant. So this is Boltzmann constant here. Each degree of freedom has energy half kT. Then total gas, kinetic energy of the gas associated with each degree of freedom, half NKT. Now you can see that Na into K, Na into K, Na into K means what? R. So each degree of freedom for the gas becomes what? Okay. For gas, each degree of freedom has what energy? We can see that. Half RT. Okay. So if we talk in terms of monoatomic gas, diatomic gas, polyatomic gas, note this first. Okay. Note it first. Right. Done that. Okay. So then let's talk about internal energy of monoatomic gas. So internal energy of monoatomic gas. So how many degree of freedom? Say 3. 3 degree of freedom. Okay. So 3 degree of freedom, and each degree of freedom has how much energy? 1 by 2 RT, right? So 3 degrees of freedom. So shall we write a formula first, and then degree of freedom we will associate with that. Okay. So instead of writing monoatomic, let's say internal energy of gas. Okay. So each degree of freedom has how much energy? Half RT. Multiplied with degree of freedom. And if there are n number of moles, then NF into 1 by 2 RT. Number of moles, degree of freedom, and each degree of freedom has how much energy? Half RT. Now we will say monoatomic gas. Okay, so for monoatomic gas, how many degree of freedom? 3. So N into 3 by 2 RT. This is number of moles. Diatomic gas. How many degree of freedom? 5. So 5 by 2 RT. Okay, polyatomic gas. How much degree of freedom? 6. So N into 6 by 2 RT. So that means N into 3 RT. Okay, so this is internal energy. Okay, so today's class we are finishing here. Next class we will start from internal energy only, and then we will proceed on to the first law of thermodynamics. Okay, bye bye.